Good afternoon. My name is Dieter Steinhauser, accompanied by Trevor, and this is our ROS 2 final project for the University of Florida Autonomous Robots course. The purpose of this project was to simulate, visualize, locate, navigate, and map using the ClearPath Jackal in ROS 2 Humble and Gazebo Fortress. The purpose and application of this was to mimic some of the features of P-AgBot by Kate Kim, seen on the left, of Purdue University. They're using 2D and 3D LiDAR to map and estimate corn height and corn stalk radius with their sensors. We were not able to get to this exact point in our work, but we got the core feature set down so that we may better understand and collaborate with our peers at Purdue University in our Engineering Research Center, IoT for Ag. A full list of our instructions are in the README, but I will give you a quick overview of what we did as well as give you a short demo as to our results. I took an old gaming computer and installed Ubuntu 22.04 for first time setup, allowing RDP connections so I may remote into the machine. Installing the NVIDIA drivers so that we may have GPU support for the Gazebo launcher and RViz was pretty pertinent. After that, I installed ROS 2 Humble, going through their first time setup. Very simple. Beyond that, we had to install Gazebo Fortress. After this, we installed the ClearPath simulator, in which we were able to import and set up the configuration for our specific ClearPath devices and the sensors that are on them. We were able to launch the simulator, getting rudimentary movement going and visualizing where our sensors are on the robot. For reference, we also have our robot.yaml in the README, just in case, because the robot.yaml is located in the ClearPath folder, and you must edit it outside of our repository. Our sensors that we used was the Hoyoko UST 2D LiDAR, as well as the Velodyne 3D LiDAR. I believe it's the VLP16. We were able to interact with RViz and get 2D and 3D LiDAR outputs, while also commanding it via a bridge node. In this, we have a quick demo and implemented circular motion of our robot having to publish to the command velocity topic, as well as recording the movements, the output of the sensors of 2D and 3D LiDAR. From there, we installed Nav2 and learned how to use it a little bit more, and then created a demo in which we can navigate, localize, and map with the Jackal robot. We also created a waypoint following system, but it's not working in its current state. So let me demo the full setup at the moment. I have 5 working terminals, launching Gazebo Fortress, RViz visualization, Jackal localization node, a Jackal navigation node, and a Jackal slam node. Now, as you can see, we have the simulation of the Jackal robot in the warehouse, as well as the progressively mapped, or rather, simultaneous localization and mapping on the right side, and navigation goals completely responsive. SLAM does take a minute to update. I think this is one, a limitation of the hardware, and two, a real-time issue. We intended to use this simulation with a waypoint following system in which we would pre-program route coordinates so that the Jackal would scan the rows of the warehouse or the cornfield consistently with a given path. To do this, we created a pathfinder.py. In it, it is a visualization as well as a marker creation in which it creates pose stamps for the nav to the waypoint follower system. So we were not able to get this working, but I will launch the waypoint, the nav to bring up, in which the waypoint follower will listen. And run pathfinder.py. An output of the warehouse is given to us. This map is a PGM generated by SLAM, performed in the map, in the simulator, and we've configured it in such a way that we can put a certain amount of waypoints down, and it will can follow them consecutively. So I believe I have 6 waypoints in this configuration based off of the pathfinder.py code. Intermediate waypoints are blue, and the final waypoint is red. The starting waypoint is where the robot starts at, and it is green. Currently, the requests are being rejected. This is certainly a limitation of the system. If we had more time, we would expand and figure out what is causing this rejection, as well as change the world towards the agricultural crop rows, targeting corn and or peanuts, whatever is more applicable for our research.